All right, getting the stream started again after a lot of yak shaving, new equipment. So hello again. Hi to everyone joining on YouTube on my usual channel. Oh geez, I need to mute that. Well, apparently the streams are working on Twitch and YouTube, so that's part of what I wanted to test with this stream. Let's actually switch to the camera. Hi. So yeah, so I've been wanting to try streaming to multiple services. So long story short, I'm doing that now, and so this is on my usual YouTube channel, plus my day job, Sanrio, who I do hardware reverse engineering for. You know, I talk about a lot of the stuff that I do there publicly, and there's you know, there's intentionally a lot of overlap between the stuff that they pay me to do and the stuff that I can talk about on my streams. So we recently just set up a Twitch channel named Sanrio Labs. So I'm trying out a setup that simulcasts to both of those right now. So yeah, it looks like YouTube's working. Can't quite tell if the Twitch stream is working right now. Pardon me while I reload this web page and see if this is successful. It's I should have enough upstream bandwidth for this. So bear with me while I try something experimental. And yeah, the other announcement is that the video quality should be a whole lot better, because previously I was like super CPU limited. Yeah, it turns out that the CPU that they put in Mac Mini is not quite as good as a quad i7 for 4 gigahertz, which is what I've got that's running on now. So yeah, super nice. Had enough. Oh man, Tuco just did a pretty aggressive jump. He's been hanging out on top of the audio interface, which always concerns me because I can always see him like adjusting the levels, but so far that seems to be all right. Yeah, it looks like the video is smooth on Twitch and on YouTube, so we'll have to let me know if there's a problem. I think I can see the chat for both. So, experimental territory ahead, but yeah, so basically I kind of gutted my video setup over the past couple of days and put it all back together, and had to, you know, of course, rediscover all the random little bugs, like this video interface doesn't like this signal, and you have to make sure that this is forced into that mode, and you have to put these HDMI splitters in this order and not that order, or else you get glitches sometimes. And you know, all that stuff changes when you change the setup slightly. Yeah, I started to actually diagram this out. I think I have like a partial diagram of how this stuff actually connects to the broadcast setup. Maybe I can get this on my camera. No, that's where I already am. Oh yeah, and I've got enough CPU free to do deinterlacing, I think. Although what's weird is, for the DSLR, when I optimize the deinterlacing settings to look best for the actual, the picture itself, so when I move the camera around it doesn't look blurry and the still images are pretty clear, that seemed to really mess up the on-screen display, so I'm guessing there's just something weird about how they're doing the on-screen display in the HDMI output. But yeah, I was starting to diagram this out because I thought, oh, it'd be great to have a diagram of how everything's connected. But then, you know, then it's like I started seeing the differences between reality and my my ideals of how things would work. The first difference was that so on this new computer, I upgraded from a Mac Mini, which was just really underpowered. Both the CPU and the GPU were not really up to the task. And in particular, I think it might have just been some interaction where something that Open Broadcaster was doing on the GPU might have also been incurring a higher than expected CPU penalty. And the upshot of it was that just with all the compositing and decompressing and moving streams around that I have this thing doing, it was just totally maxed out on CPU. So I had to downscale a bunch of the inputs. I had to run both of the webcams at a really low resolution, and I had to do the output at 720p. Whereas now I can have it like composite everything at like higher than 1080p, like 2560 by something or other. And then and then output 1080p, and then there's enough CPU to spare that I can use a nicer software X264 encoder, and so. And then right now the bitrate is actually limited by my upstream minus a little bit of overhead divided by 2, since I'm streaming to 2 destinations right now. And I guess theoretically I could put that server in the cloud somewhere, but right now it seemed... I'm about to upgrade my internet to fiber because I'm really, really tired of Comcast's... anyway, that's a long divergent story, but I hit their 1 terabyte bandwidth limit and they started injecting annoying and usually broken warning dialogues into my connection by like man-in-the-middling my HTTP. So, it's a good lesson for why you should HTTPS things. It keeps your ISP from breaking your web pages. Anyway, I started to diagram this thing out and it was super incomplete, but like there's all these sort of signal chains where like this thing that I call Fishbowl is the computer that I run the demos on. It's like a Mac Mini that is at least fast enough to run VMs and all the kind of example software and like OSCOPE stuff that I'd be doing. And then this Fishplex thing is the thing that I added afterwards once I had got this signal path set up for the Fishbowl computer. And then I was like, I've got this extra HDMI multiplexer and I want to plug other things into this. And that was also when I started wanting to stream the Rhino CAD stuff, so I needed my computer. I needed the other computer that had the Rhino license to actually have access to stream. So anyway, that's just an HDMI multiplexer that lets me connect this signal chain up to other things. But then I want to split that so I can monitor it in real time without any delay. And then I split the audio off using a separate little audio splitter dongle, and then that goes through a ground loop isolator because these HDMI signal chains are really noisy and I want to keep that away from my audio interface. And then that goes into the audio interface, which mixes it with the microphones and processes it, and then re-outputs it and records it. And then to get that video in, so I ended up wanting a bunch of video channels because, it's nice to have, for doing electronics, you need at least like a camera for small things and a camera for big things. And I've, so with the Mac Mini, I had this setup where I was using 2 of these little Blackmagic adapters that went from HDMI to Thunderbolt. And they were pretty good. They're a little finicky about video modes, not quite as finicky as what I replaced them with, unfortunately. They do a pretty good job. The problem is, I got one of those at first because I used it with my laptop, or I've got one of the crazy trash can Mac Pros, and I use it with that too. And so I'm like, oh, I'll just get another one of those, and then I'll just get a computer to plug those into. And so I ended up locking myself into Thunderbolt, and the fastest computer I had available with Thunderbolt was one of these Mac Minis. So anyway, I ended up replacing that with another Blackmagic card with PCI, a PCI Express card with 4 SDI inputs. And that seems like a pretty nice piece of hardware, but the SDI HDMI, conversion seems to have some finickiness. Plus, I think there's some finickiness with the modes already in the Blackmagic drivers. So that's what the camera is using right now. But for the computer, I want that to handle lots of different video modes. So I've found that these, either the Magewell USB HDMI adapter or the cheap knockoffs of it, they both seem to have really good ability to just take in whatever random HDMI signal you throw at it and then scale it into something the computer can deal with. So I've got one of those for the kind of Fishbowl computer that's always changing modes. But then, I still get USB webcams for the desk and my cat, which he's back, by the way. I should bring the camera over. watch my cat in HD. I mean, this camera is still kind of annoying. This is possibly something to replace. Anyway, so the upshot is I've got like 4 SDI inputs on this machine now, which I can use for up to 1080p, 60 frames per second. I'm using one of those successfully for the camera, but I've been with the really cheapest SDI HDMI converters that I got, I've been unsuccessful at getting a lot of the inputs that I have to work with those. So I tried ordering some slightly less cheap converters to see if that helps. But yeah, in the meantime, I'm only actually using one of those SDI inputs. And then I've got 2 USB 3 HDMI grabbers on that machine for the microscope and for the fishbowl computer. And that actually is kind of a nice use for the microscope, or a nice way to get the microscope signal in, since that Magewell adapter does have the nice property of doing deinterlacing in hardware. And the microscope that I'm using gives me 1080i, which is kind of annoying, so that was like one of the big CPU drains before. And I've got enough CPU that that's probably not a big deal now, but anyway, hope you enjoyed the impromptu tour diversion. I think we should get back to the actual stream now that my cat's in position. Make sure the output quality is reasonable at this juncture. Okay, looks like the streams are kind of good. I've got one report from Twitch chat that the audio on there might be out of sync. I don't know much about what I can do with that right now, but I will have to check the archive later to see if I can optimize this. But in the meantime, I apologize if it's out of sync. So let's take a look at this setup here. Oh, maybe let's take this a little further away from the microscope. Okay. So, you may have seen, or heard of this kind of voltage glitching technique. Or, more generally, I'm working on fault injection. So, trying to get a processor to take some execution path or kind of corrupt some data in some way that wouldn't normally occur or would be very unlikely. But by introducing changes in the external environment of this chip, I can cause otherwise very unlikely errors to occur at exactly the right time. And so in this case, I'm trying to use that to develop a technique for extracting firmware from these chips. So this is this is kind of a stand-in for the microcontroller that I would be reading back the program off of. And so the real device I'm trying to develop this technique for is sort of like an Internet of Things, programmable logic controller, sort of an industrial Arduino kind of device that you would use to attach things to a network and then control them potentially remotely. And it's based on this microcontroller that's relatively advanced. It's got a fast ARM Cortex M4F core in there that usually runs at 120 megahertz. It has built-in Ethernet MAC and PHY. It has a lot of great peripherals. So in this case, this is running an example that I've configured to be pretty close to what I think one of those actual PLCs that I'm investigating is actually doing. So it's got it's got a modified version of this example that runs the LWIP, TCP/IP stack and web server, which is what this PLC runs, and I'm running it at the same PLL frequency. I've made a couple of small changes to just try to get it to bring up a little faster. Like I've tried disabling Ethernet auto negotiation and hard coding it to 10 base T, which is what I'm using here. Excuse me. Important to stay hydrated in the winter. Yeah, so this chip has a built-in Ethernet MAC and PHY that can handle 10 base T or 100 base T, and normally it'll go through an auto negotiation process. I wanted to hard code it to 10 base T. Well, I did a bunch of experiments to try to get this chip to underclock as slow as I could while still communicating with it over Ethernet. And you know, it's certainly possible to develop like this part of the glitch exploit using you know, some communication method other than Ethernet. And I've considered the merits of making another version of this test harness that just looks for glitches just using the serial port to report back. But right now it's configured really close to how the actual device would be configured. And I think it's probably worth keeping Ethernet in the picture as long as it's tolerable to, because it really does seem to be kind of the weak point in a lot of the stuff that I'm doing with like the clock and the power supply. So you know, for example, I was trying to underclock this to make it as easy as possible to generate glitches that are sharp relative to the clock rate of the CPU. And the slowest I could get it was a core frequency of, you know, down from 120 megahertz to 27 megahertz. And the limitation there seemed to be the Ethernet PHY actually. Like it seemed to be causing like weird analog oscillations in the current drive signals that came out of the transmitter. So yeah, I tried to get it tried to get past that a little bit, but yeah, right now that's my lower limit. And you know, I've tried to make the Ethernet a little bit easier to work with. You know, I thought 10 base T would be easier than 100 base T. I also thought it would let me underclock a little bit deeper. I did manage to verify that. You know, I tried underclocking with 100 base T, and it actually didn't go nearly as far down as I could get it with 10 base T. I forget the exact number, but yeah, it was something like, I mean, it was pretty easy to get an underclock of like 25% with 10 base T, whereas with 100 base T, I could get it barely down to half, I think. And it's also much easier to deal with the electrical noise produced by 10 base T, since I'm looking at the power rails to get an idea of what's going on inside the processor. And 100 base T just continuously transmits symbols when it's idle, which is, you know, as you can imagine, super noisy when the Ethernet MAC is built into the same system on a chip as your CPU core. Whereas 10 base T only transmits these very, you know, intermittent keep alive signals, you know, every 100 milliseconds or something. So it's a lot easier to deal with. Let's restart this camera before it decides to restart for me. All right, so where were we? This is a mock-up for this glitch exploit that that's intended to extract firmware from the device. My theory for this is that, you know, if you look at the source code for the HTTP server that's running on here, it's serving all of the static files, like, you know, your index.html and your JavaScript files and all that. It's just serving those out of a kind of pre-baked data structure that gets compiled into your MCU's flash memory image. So, you know, there's this one lookup process that goes through and, you know, tries to find a match for the file name and fills in this structure with, you know, it fills in this structure with a pointer to the file's data, the file's length. There's a lot of opportunities for that to get corrupted, and if you corrupted the pointer or the length or the pointer to the structure, then you could get this whole process to just return some other arbitrary chunk of flash memory over your HTTP connection instead of the index.html or whatever you asked for. So that's the goal. And one of the steps in getting there is having a glitch that I can use reasonably reliably to, at a particular point in time at a particular point in time kind of get the processor to misbehave in some way. And there's a lot of ways that this could work, a lot of ways that it could be made to be useful. So, it could skip an instruction, it could write the incorrect value into memory, it could read something incorrectly into a register. And at a lower level, this tends to happen via, at a particular point in the cycle of an instruction happening, as the logic is propagating through, you can cause a very brief pulse that can cause, some energy transfer into part of that circuit that flips some bits. And by controlling the timing very precisely, you can try to target it to, a particular kind of glitch. So, I'm somewhere in between having some idea that glitches are possible on this setup and having something that's repeatable. So I reached this milestone recently that was pretty exciting, where so I'm running a very simple mock-up on here where, it's kind of like a sponge for glitches, where it just runs a for loop that fetches a value from memory and adds it to another value in memory, and I use volatile variables to be sure that those are always read and written to memory, at least at the compiler level. I don't think I have to worry about data cache on this processor. But even if it is written to data cache, that's probably useful to have in this model. Anyway, I have this little example that just tries to soak up glitches, and I have managed to, I think I got maybe a 1% success rate at glitching it in a way that changed the resulting value of those counters, so indicating that some of those loads or stores or increments or instructions somewhere along the way got corrupted. So that's kind of a starting place for looking for glitching parameters. That indicates that it's probably possible to get the behavior I'm looking for using just VCC glitching. So far I hadn't really seen nearly the response to VCC glitching that I was used to from the last processor I tried this on, which was a slower 8-bit processor. But I think a lot of that is just the kind of more challenging electrical environment of creating pulses as narrow as I'm trying to create. So, this processor is still running at 27 megahertz when I'm trying to glitch it, and, ideally I would want control over periods that are, like an order of magnitude narrower than the clock period. And I don't really have that, but I'm getting around like 10 or 20 nanosecond edges with this setup, which seems like it's enough apparently. So now that I'm getting like a non-zero success rate with these glitches, I can tell that electrically this setup might be good enough, and it's kind of a starting point for honing in on what those actual glitch parameters are. Right now the glitch setup is a little bit slow and suboptimal, so part of this might be just trying to optimize this so that I can run the tests more quickly. Since right now it's, it can easily wedge itself in a state where it just stops responding, so I was thinking about adding a watchdog timer since, well, the actual hardware does have a watchdog timer also. I also might very well want to add an explicit reset. Right now, this doesn't have a target reset, but it probably really should. I just push the button manually if I notice it gets stuck. So anyway, let's get this set up and just take stock of where we're at right now, and then look for improvements. I'm going to get some tea, and I will leave you with the Tuco cam while I refill my tea. Now in the Hest of Ds. Well, if the autofocus would cooperate. There we go. Wow. I wonder if this camera just doesn't like being on such a long USB cable. That is one thing I could do with all these extra SDI inputs for sure. Okay. Great. Let's get this whole thing going. So, yeah, where do we even start? So these are actually already going. That's the Raspberry Pi and the kind of remote control Ethernet adapter that it's using to talk to the other microcontroller. So this microcontroller is really just being used as an Ethernet adapter to talk to this in the same language when they're both slowed down to the same degree. And then I'll be SSHing into this Raspberry Pi to run a proxy server on it. But the first thing we need is the clock source, which is provided by this Chip Whisperer board. So that was on here. And this is a handy VM that the Chip Whisperer folks provide on their website. I guess it had gotten shut down. Usually I just keep it suspended. Is this some kind of Linux power management fail? No? I guess I'm just impatient. Alright. I am impatient when it comes to Linux booting and not giving me a screen full of text. It's kind of weird. Anyway. So, this is my startup script. Well, I'm going to need to modify a bunch of this. Let's just keep this open, but let's just start by running what we have. So this script will start up the Chip Whisperer UI and configure it in the way that matches this experiment. So it'll set up the clock generator, and it's set up to run the experiments over HTTP via the Raspberry Pi's proxy server. And it's also configured to be generating glitches, which I'm going to disable for now until we've verified the other part of the setup. There's some kind of weird gamma issue on this. I'm just noticing that I can see the gray bars on this table just fine on my regular monitor, but on the stream output I'm seeing it really washed out. I'm wondering if there's some color gamut setting I can fix. YUV color space. Oh geez, yeah, somebody's got like a buggy YUV conversion going on here maybe. Huh. That's not an improvement. Okay. I think, oh man, how is digital video still so hard to get the colors to come out the same? I mean, I'm sure this would be easier if I was using just like all professional hardware, but then this would also cost like 100 times as much. Okay. I don't know why the colors are slightly washed out, but I guess that's the way it is. actually know if the ADC can go that fast on the Chip Whisperer, but it says it's going at 185 megahertz. Might be more. Yeah, that's better. Sometimes that just ends up locking to the wrong value. I don't know if that's like a UI bug or what, but yeah, that's the right frequency, 108 megahertz. So we should be seeing the clocks running at the right frequency. So this is generating a 27 megahertz clock now. And then the next step is I've got this little FPGA that's doing some clock conversion. So that's the Chip Whisperer, and then the FPGA board is actually under the one that looks homemade. Pardon that creaking noise. That's the noise that tells me I really gotta clean out the bearings on this thing. So, yeah, you can't see a lot of the LEDs there. I would move it, but it's not really important to see all the LEDs because they just blink a lot. But the fact that they aren't blinking indicates that the clock isn't actually coming out of that which is what the other devices need. So, need that clock gen. So this uses the wonderful Ice Storm tools. So I think what I need to do here is to remove the Apple FTDI driver. I really want to show what's under there a little bit better. Move this slightly. I think I also need to move this microscope arm out of the way. That wasn't good. Excuse me. Yeah, that's a better view. So, yeah, you can kind of see some LEDs on the left side, especially if I tilt it. And the big chip under, directly under that circuit board that's covering it is an FPGA. That's a Lattice Ice40 series. And then it's a little FTDI chip there that's being used mostly just to program the FPGA. So in this case, I need to unload Apple's driver for that FTDI chip so that I can talk to it directly. So I can use kextstat to look at the kernel modules that are installed. Some good old buddies here. Anyway, there's a lot of fun stuff here, but we could actually just grep this for FTDI. So that's what I'm looking for. This is the bundle ID for the FTDI driver. So I'm going to kext unload that. And we should have access to that device. If I gave it the right file name. Cool. So now you can kind of see the lights blinking. Oh, sorry, Tuco. Yeah, that middle green light indicates PLL lock, and then the other lights are just blinking in a counter pattern, binary counter. So that's generating the other clocks that we need and distributing them to these other boards. So now the other boards will respond, which means we can start actually trying to communicate to them. So we should reset them both, because it's good to reset a board after you stabilize its clock. And then let's get the Raspberry Pi and this board talking to each other. So I think that's all set up to load again. Oh man, we might have to figure out what this Raspberry Pi's IP address is. Yeah, maybe let's actually attach a console to this Pi so that we can get its IP. I thought this was its name. It could just be bad MDNS karma. MDNS hates me. I've got an okay relationship with HDMI these days. This adapter gives such interesting glitches. I might have to reset this Raspberry Pi. Maybe this Raspberry Pi has just crashed. Maybe that explains everything. I might have been careless about some voltages on this system earlier. There we go. Now we get to watch the Raspberry Pi boot. Some nice residual DRAM contents. Well, let's see if we can just SSH into it now. Yay! I guess I just needed to reboot it. Always the solution, apparently, when the hardware is crashed. Okay, so... Oh, I don't need that core dump, do I? Oh. Oh, that was from GDB crashing. I don't really care. Okay, so I'm just gonna run this. And so now it's waiting for the microcontroller here to detect the Ethernet link, which it isn't going to do until I plug this in. But so this micro just needs power. I can't plug this in until it's powered, because otherwise it'll start to be powered over the Ethernet cable, since I removed any AC blocking that might have existed, which isn't usually a good idea, but it was for an experiment. Anyway, let's power this up. So I've been powering this whole contraption off of 12.5 volts, because that's the maximum that these MOSFET drivers can handle. And then I'm just, this linear regulator on that yellow breadboard. I really just shouldn't talk while I'm moving stuff around because I can't use any of that and you probably can't hear me. Yeah, so I'm bringing in 12.5 volts here. 12.5 volts from a bench supply, something nice and stable, and linear regulator, again, because I don't want any switching noise in this part of the circuit. And the current's not too bad, it's like under 100 milliamps, so this doesn't get super warm. And this is just monitoring the input voltage, just because I had some of these handy and they seem neat. So the 12.5 volts powers these MOSFET drivers, which it uses to bring the gate voltage of those FETs up and down and past the threshold voltage as fast as I can with this circuit. And then the 5 volts generated here goes through this wire into this board where it powers. There's a 3.3 volt regulator somewhere on here. I think it's one of these small chips. And then there's an onboard 1.2 volt regulator on the microcontroller that generates the core voltage that we're actually trying to glitch here. So I talked about this in an earlier stream slightly, and we actually built it in a stream. This is sort of a glitch adapter board. It's a little bit like a motor driver, except it's really intended to just have fast edges. So I have these 3 MOSFETs here that are kind of alternately turned on. The middle one is normally on, but it's turned off during the glitch. And then during the glitch, either the left one or the right one is turned on momentarily, depending on these jumper settings. So with the left MOSFET on, it just drains the core voltage capacitance to 0 as fast as possible, just shorting it out. If the right MOSFET is on, then it actually dumps some voltage from this little capacitor bank into the V-core rail, so I can use that for higher voltage glitching. Right now I've been using the ground glitching so far. And then these are the MOSFET drivers, and that's just a logic chip, a couple of Schmidt trigger inverters for buffering the input signal. I did end up having to take off the MOSFET from my chip whisperer. Can I just slide that? Yeah. So this wire is where I'm tapping the drive signal that would have gone. Yeah, this is where I'm tapping off the drive signal that would have gone to the little 8-pin MOSFET here. But the MOSFET itself was just too much of a capacitive load and it was slowing it down too much. So yeah, the easiest solution there seemed to be just desoldering the MOSFET. All right, let's power this thing up. Oh, yeah, some good, trying to catch up with the chat. Yeah, it looks like I might have an encoding problem. YouTube is complaining that my keyframe interval is too long, and so I probably need to change my settings. And that, or something related to that, might also be causing the Twitch audio lag. So, yeah, I don't know if there's anything I can do about that during the stream, but well, that's why we have tests. This will be a relatively short stream anyway, and I'll try to improve things for next time. And yeah, I also saw a great suggestion to tag the stream with electronics, which would be great. Okay. So I need to be giving this more than 5 volts. Well, I don't need to, but I want to. This will make the edges faster. So I'll give this 12.5. And just enough current limit. Because, you know, I was not too careful in designing this to avoid shoot-through, which is where the MOSFETs create a direct short between your power supply and ground. And, well, I mean, it wouldn't create a shoot-through on this power supply. It would, at worst, cause the problems on this external supply, which I'm not using, so yeah, I don't know. That should be fine. Anyway, it's always good to have a current limit for safety. Alright, so this microcontroller now has power and clock, which is good. And I'm going to turn on the O-scope so we can start monitoring its power in a little bit more detail. So these two SMA connectors here, I soldered those onto the vCore rail on the CPU. One of those is going to the A to D on the chip whisperer, and the other one's going to my scope right now. And I think this is set up with triggering right now. Okay. So over there we can see our vCore rail acting pretty normal. Which is to say, kind of noisy, but it's fine. We kind of want to measure the noise, so I haven't really worried about well, there's different kinds of noise that I do worry about, but this particular thing is fine. Mostly I just want to know that the glitch circuitry is not inadvertently doing something bad to the power rails right now. Okay. So, now we should be able to get an Ethernet link. Great. We got packets going back and forth. Now let's do this. Great. So that's the test program running. Let's pull up the source code for that. Oh, geez. That video interface certainly does weird things when there's no signal. Alright, Twitchception. Okay. Oh, geez. That video interface certainly does weird things when there's no signal. Okay. Oh man, what program? Okay, right. This is all built with the crazy TI IDE thing. It's like Eclipse, but worse. I've tried my best to get it to use the files that are in my Git repo outside the VM, but oh man, I thought I already had this stuff open in here in a way that was... I remember this having a really weird metaphor. Like, I thought I already had this set up to... Oh, that's what I needed to do. I thought I already had that set as the default. I don't know why it opened up with a different workspace. Well, I clearly don't know how to use this IDE, but I think we can just open the source code anyway. Yeah, it has such a weird notion of how project files work. Like, I thought Visual Studio's project files were weird, but this is even weirder. Anyway, I think the relevant thing is in here. So again, in the spirit of trying to have an example here that's as close to the real thing as possible, while still remaining relatively convenient, I didn't want this to have the full like in-memory file system, and I also didn't want this to have like a CGI or anything else complicated. Oh yeah, Visual Studio, sure. Open another IDE. Yeah. Anyway, I kind of hacked this test into what would usually be the file system code. So kind of gutted this file, and when you open a file, it allocates a buffer, triggers a GPIO pulse, asks you to create an account. What is going on? Oh god, I don't even need this. I just wanted a text editor. I guess I don't have... Oh, I do have Sublime Text in this VM. Great. That's what I wanted in the first place. Alright. Oh, we don't need this sidebar garbage. Great. So, as I was saying, we have this kind of gutted file system implementation. And so this is what normally sits behind their kind of example HTTP daemon. And so normally this thing serves up your index.html and your JavaScript. But in this case, no matter what file you ask for, during the open operation, it allocates an internal file system structure, which is normal, but it also allocates just this buffer for some static file contents, and then it runs this experiment. And so that's what we were seeing the result of in curl just a bit earlier. So it's just pulsing an IO pin really briefly. Then these are the loops that are intended to be easily targetable by the glitches, or at least by glitches that would be useful for just kind of causing control flow havoc in an MCU. So in here, I just have some of these numbered variables, and I'm just adding this other variable called increment. And those are all volatile variables that the compiler should keep in, probably stack memory. And we could disassemble this to see exactly what it does, but this should be fine for our purposes. So right after this trigger, we start running these loops, which will normally all return 100,000. But if we glitch if we glitch any of these loops, then they'll return different numbers. And then we just format the results in a simple HTML page. And then also, I've been seeing a bunch of glitches which, instead of causing this to return different results, they cause a 404 error, which is what you'd get if you returned null from this function. So I think, yeah, I think what I might be doing with that glitch is, causing something else to go wrong in here that causes it to pop a stack frame somehow, which is interesting. And then this is just kind of a gutted implementation of read that just returns data from the buffer and advances a count. So I'm not going to bother getting the IDE working, but you can trust me that that's what's loaded in Flash on this processor right now. Okay, is this still working? Yeah. Great, so every time this runs, besides giving us the results, we also get a trigger signal, which I think is still hooked up to the O scope. Let's try that. Yeah. Sad bearings. Okay. So there's not much there on the scope right now, but if I run curl, it's triggered. So that yellow trace is just the core voltage rail on the CPU. And if we zoomed in significantly more, we could start to see some CPU activity. Let's try doing a little bit of that. It's usually a little bit more practical on the Chip Whisperer. I have the scope here mostly for checking out the really wide swings in the voltage glitches. Let's also make this AC coupled. And let's just start doing this in a loop. So some of this is noise, but some of it's, there's some stability there. The stuff that's stable from iteration to iteration is the signal we're looking for, and the other stuff is usually not what we're looking for. And so I think a lot of this is not super clean right now because I think I'm still seeing a lot of oscillation due to the voltage regulator not having, enough capacitance really close to the regulator. But, it's enough where you can start to pick up some gross patterns, which is all we really need this for at the moment. So mostly I was using this to evaluate glitches. Oh, that's interesting. So there's a 404 without any glitches whatsoever. I wonder if that wasn't a glitch. I wonder if that's memory exhaustion. That's interesting. Well, maybe one thing I can do to improve reliability is just to have this thing reboot itself every couple of iterations. I don't really care about debugging memory leaks in embedded HTTP code right now, and I was planning on having something like a watchdog timer anyway. Yeah. Well, darn, I was hoping to avoid having to recompile this anymore, but I guess it does still need some work. And I guess that's a good baseline test to remember to run this in a loop without actually glitching it, just to make sure the app doesn't die on its own accord. So if I reset that, then this goes back to link is down. Should come up in a sec. And now it's back. And then I can go back to this. Yeah, I mean, this is part of the annoyance of the Ethernet environment, because ideally I would have just a clean reset before every single test, but it's still taking a while to do the auto negotiation. Well, some kind of negotiation. I have the PHY, like the speed negotiation disabled, but there's some delay between actually initializing the Ethernet controller and detecting a link that I haven't been able to track down quite yet. So that would be super annoying if I had to reset the whole system before every test, even though that's really good for reliability in terms of reliably finding these glitches. Yeah, that seems to be about the same amount of time. I was just going to also take a look at this pattern on the scope. I think this, oh, no, it just changed, but I mean, the easiest solution to this and potentially the highest throughput would be to just have the test harness reset the target when it detects like a 404 error or something similar. Anyway, I was going to point out what I think are the Ethernet transmissions. I think these larger spikes are Ethernet related. I mean, we could find out for sure by putting up Ethernet on the other trace. Yeah. Well, I do think it would be most reliable to just add a hardware reset to this, which, I could use anyway. And, I mean, there's a bunch of ways to do that. I think the Chip Whisperer has a GPIO that is relatively easy to configure for this sort of thing. So maybe that's the easiest way to do this. Like, I think some of the existing Chip Whisperer target scripts have a reset using one of the GPIOs, and I might just be able to copy that approach. This is the simple serial module for Chip Whisperer, which I think has, well, I was going to say I thought that had reset support, but maybe it's one of the subclasses of this. I'm just going to do a grep. So we have these 4 target GPIOs, and I think I'm only using one of them right now. I think I'm just using the trigger. Oh wait, no, yeah, the trigger is a separate thing. The trigger is one of the high-speed IOs that go to the FPGA. The GPIOs are separate. I think this is what I want. I don't know how this part, like what module this is for, so maybe some grepping of the source code is in order. That's called NRST. Presumably because that's the name of the electrical signal you'd usually attach it to. Yeah, that doesn't really give me any hints, huh? I mean, that looks like a separate GPIO and not something you can attach to these GPIOs. Oh, maybe this is just how I actually control them in Python, is by changing these values. I don't know what these are for, but I guess these are probably internal signals on the Chip Whisperer board. So I think I just want to use either IO3 or 4 for this. Let's get a pinout. Pinouts are great. And then we can have this just automatically reset the board when it gets into a state like this. I should just duct tape this pin out to the wall or something. Yes, yes. Okay, yeah, so the triggers are overlapping with these. I was getting the trigger inputs confused with these high-speed pins, which are just used for like clock and glitching. So I guess that pretty much narrows it down. I'll use target 3 for the reset. Let's just make sure I can control that. 1014. Let's get a jumper for that. Oh, that's the view. Orange is an alright color for a reset. Yeah, okay. It's right above the trigger input. That's easy. And let's just use the scope to check this out. Alright, 5 volts. I mean, 0 volts on a 5-volt scale. Alright, so that's 3 GPIO. Great. Got ourselves a cute little 3.3 volt IO. So I'm just gonna have that pull a transistor that yanks the reset line low. And then I think we can just do this in Python. Like issue these 2 settings. It's a little off screen right now, but maybe I'll just turn off the overlays briefly. So as I change these in the Chip Whisperer UI, it keeps a running list of all the kind of machine-readable versions of those changes for easy introduction into scripts. So I think that's going to be the next step after building a circuit for this. I also need to look up a good place to attach reset to this board. I'm guessing one of these pins sticking up for the launchpad connector already has it. Okay. Such cat. Alright. Let's find documentation for the other pin that I need here. Ooh, we could also watch Vaporwave. And the setup here, I was using like a bunch of like Vaporwave videos and stuff to like check it out. And it's just, it would be a great way to do like a Mystery Science Theater 3000 kind of thing. Except that also would be a wonderful way to get just totally taken down by YouTube's copyright bot. Oh, you know, that's right. I think the easiest way I had to get these pinouts was actually from the Eagle CAD files. Oh no, now it's opening in PCB new. That's... Oh man, these extensions are so generic. Okay, this is upside down relative to how it's laid out on the table, and I don't see an easy way to change that. But anyway, just imagine this flipped 180 degrees. This is the Ethernet connector, it's the processor, it's a debug interface, and I just want to find something that's attached to reset on one of these somewhere that's easy to access, basically. Yeah, I think these two connectors and these two connectors are the ones that have long pins, so that would be nice. And there's a reset button like right next to, yeah, target reset. That's what we're looking for. Oh, that one is super inconvenient, actually. That one's underneath where I have the glitch circuitry wired in. Is there a copy of that elsewhere? Not on that connector. Not on that connector. But here I can get it. Great. So you can verify that this is reset by grounding it and watching the chip reboot. I don't think that's right, actually. Oh, yeah, I think this needs to be the top row. Otherwise, it's just some random GPIO pin. That's reset. Give this camera a better view of the LEDs. Okay. There we go. That's the shot I wanted. Okay, now I just need some kind of transistor. Doesn't really matter what. Let's grab something that's handy. I really need to redo this with the new label maker. This one is super faded. See that? Oh. That isn't even the actual label. You're seeing it like backlit, so it says Signal BJT, but actually the label says MISC BJT. Oh man, I might actually have to take this apart quite soon to fix it. Man, that actually might be a problem for the stream. I might have to take apart my camera arm and fix it because it's kind of seized up right now. No, if I just kind of hold the camera. Yeah, super faded, and maybe there's a transistor in there that we can use for this. I think a 2N3906 will do. Let's get a refresher on that data sheet. Oh man. Yeah, got a good catalog of glitches for this stream. Looks like some audio sync issues, some encoding issues maybe, and now I actually really need to take these bearings apart and clean them. So, but let's see if we can at least like get this reset happening. Oh man, this is bad. I should maybe take the camera off of this arm until I can fix the arm. Hello, camera. I just need to put the arm somewhere where it's relatively out of the way, but the wire is still long enough I can sit the camera down on the table. Okay, that'll have to do for the moment. Get some crazy camera angles on account of equipment failure. Alright. Just need a humble transistor datasheet. So since this is a BJT, we will need a small series resistor for the base. Since they act as a current amplifier, we need some controlled current to flow into it. But not very much, so like, a couple of kilo ohms will be fine. Anyway, EBC, emitter base collector. So if you've heard of open collector outputs, that's a good way of remembering how these are often configured, because you can often leave the collector open and then ground the emitter, and then you put some current in through the base, which flows conceptual current. The electrons are actually flowing the opposite direction, but following the positive current flow, you go from the base into the emitter, or negative current flow from the emitter into the base. And then there's a correspondingly larger current going from the collector into the emitter. So that's what we're going to exploit here. We're going to have a relatively small current, which in this case, it also helps to kind of decouple the output from whatever else is going on with the circuit. Because the only thing the circuit can do is it can pull that collector down to ground. It's not going to care if something else is also pulling it to ground. It's not going to help raise it up to 3.3 or whatever the logic voltage is. It doesn't even matter what the logic voltage is here. All we are doing is pulling it to ground. So that's another reason this circuit is helpful. It's often possible to configure like the FPGA or microcontroller to have an open collector or open drain, which is the MOSFET equivalent. It's usually possible to do that in software, but since in this case we don't necessarily have access to that level of this without compiling our own FPGA bitstream, it's probably easier just to add a transistor. This scope trigger is also in the way. Is there a better place for this? I might put this on some kind of little flywire, because this does not need to be. I'm just using this for a trigger, I guess. Signal integrity doesn't need to be amazing. Cat butt. Can we get a better picture? Cat side. Cat loaf. Cat face. Alright. Scope trigger. I definitely feel like I'm at the point where so much of this is just like debugging the setup, where, oh yeah, it should totally work. It works 1% of the time. But it's possible, at least. At least we've got some proof of concept, even if it's not super reproducible yet. Alright, that's hooked up. Got room for this transistor. And let's see if I have a resistor handy that I can use as a base resistor for this. I don't think I have anything in the right range. I'm gonna grab like a 2 to 4 to 10K or something like that. I've got a whole bin of 3.3K for some reason. Alright, so the emitter needs to go to ground, and the base needs to go to that resistor. Oh, I really need a better way of doing like a ground bus for this kind of breadboard setup. Like, it's tempting to have... Well, I guess they make little, like, tiny... Because these are like the little tiny breadboards, and I think they also make power buses in the same form factor. That might be handy. Oh, let's just use a wire. Oh man, I get to make a tripod out of desk trash. Yeah. I'll probably have to wrap up this stream soon just to fix the camera, if nothing else. Okay, well, the emitter should be wired up to ground now. And... a little extension wire for the base. Alright. Can I get any of these lights on the camera from this angle? That logic is the opposite of how I was expecting it to work. Which probably means something's wrong. Okay, I know you can't see that, but I've got the scope on that I/O pin coming out of the Ship Whisperer, and it does match the labels. Oh, this is a PNP transistor. Derp. I was assuming this was the NPN version. I actually want 2N3904, which is this one. Let's just make sure that it has the same pin out. Yeah, that was just passing the signal through the reset on the target, which, I mean, I could also honestly do this with a diode instead of a transistor. The transistor just seemed like a cleaner solution. Anyway, EBC, same pin out. Okay, now when this is on, I should be seeing a base voltage of like 0.6, because that should indicate the transistor is like turning on and conducting. Much better. Yeah, now I'm getting... can I get this on the camera? I'll just hold this. Oh man, you take this arm for granted and then it's like, you have to go hold your own camera and always have to worry about whether it's like holding still or not. Anyway, I don't know if I can actually put the scope probe on at the same time. I guess if I put the other doodad on the scope, I can clip it on. There it is. Okay, that is now clipped onto the base of the transistor. Does not have an amazing ground, but whatever. So, yeah, that's looks like about 600 volts if you discount the noise. And I can toggle this with the keyboard and switch it on and off. So now if I hook the reset up, we should be able to see the inverse logic on the other side, on the collector of this transistor. Okay, much bigger voltage now. Okay, now we've got 3.3 volt logic instead of just the transistor's saturation voltage of like 600 millivolts. So now it's 3.3 volts on the reset because we're operating normally. Turn that on, and we've pulled the reset down. So, cool. So, a small hardware change to add some reliability to this. So I think that might be a good stopping point for this stream, since I've got a few things to fix in the video and the hardware here. But yeah, thanks so much for tuning in on YouTube and on Twitch, and thanks for bearing with me as I work the bugs out of a new and improved setup. Let's see if we can sign off with some full screen cat here. Oh, he's so HD. Alright, thanks for tuning in. Have a good night, everyone.